Alright guys, let's talk now about self-organizing maps, which is an unsupervised learning model. Okay, so we consider a self-organizing map, or SOM, as a visualization method to represent higher dimensional data. Usually we create this representation in one dimension. Most commonly is done in 2 dimensions, and also it can be done in 3 dimensions, but the most common one is 2 dimensions. So the idea is that as you will see with these neural networks, you can learn patterns in the information, in the data set, and you create maps that will show you visually the similarity between pairs of data points. So we usually have 2 phases in the training of these algorithms. In the first phase, the learning phase, we construct or build a map, and the network organizes itself through some steps that we're going to see, which is considered a competitive process. In the second phase is when you apply or you use this map, when you get new vectors, and you can quickly place them in the map, and based on the final location of this new vector, you can classify them or assign a category. So this is an example of a dataset with information about poverty levels in different countries in the world. And on the left side, we see a map where you can see in colors which countries have similar levels of poverty. So this map was created. This is a map considered in 2 dimensions. So you can see it is a plane. If we were talking about a map in 3 dimensions, then you will see a cube instead of a rectangle like you are seeing there. This is another example in which we are we gave random colors of pixels, and after training the map that is created show you the different colors that were contained in that set of pixels. So again, here we are seeing a map in a 2D dimension, 2 dimensions, but each of the pixels are represented by a vector in dimension 3. So you have RGB pixels. So you have some amount of red, green, and blue, but our map, our Kohonen map, is in 2 dimensions. So again, here the map is showing us the similarity in the colors of the different pixels. So this neural network is regarded as a competitive learning neural network. The idea here is that the neurons, that in this diagram, the neurons are these circles in red, will compete in a way that they will or the algorithm is going to check which neuron is most similar to a given input vector. Here an input vector is represented by these 2 green circles, and the neuron that is the most similar to the input vector, that's the one that is considered the winning neuron. And the learning is driven by which of these neurons is the winner neuron, as we will see in a moment. So self-organizing maps are considered a learning process driven by competitiveness. So the activated neuron, as I said, is called the winner-takes-all neuron, or simply the winning neuron. And the result is that the neurons are forced to organize themselves. And they are forced to organize themselves by the learning rule that we are going to see later. And every time we feed the neural network with a new vector, a different neuron will probably be activated, will be the winner neuron, and they will be organizing a bit after feeding one of the training vectors. And that's why they call these networks self-organizing maps. So every node is connected to the input in the same way, and we consider that there are not connections between nodes. So let me go back to try to explain this. So here you see these white lines. These are the connections from the input vector to the neuron, to each of the neurons. Here we have an arrangement in 2 dimensions, an arrangement of 4 by 4, so a total of 16 neurons. And here in this diagram we are showing that the input vectors are in dimension 2. So that's why we have only 2 circles here. If we were talking, for example, about input vectors in dimension 5, we would have here 5 green circles. And the information that will contain these input variables every time you feed the neuron network with a new vector will be sent. This information will send to every single node in the arrangement of neurons. And these yellow lines here are just a way to determine which neuron is neighbor of which other neuron. As we will see, when one neuron is the winner neuron, not only that one is going to be modified, but a neighborhood around or centered around this winner neuron is going to be modified. So that's why we need these yellow lines, and these are not considered connections because there is no information going through these lines. That's why we say that the input vectors are connected to every single neuron in the same way, but there are no connections between pairs of neurons. So this neural network has obvious inspiration for neurobiological studies that indicates that different sensory inputs like motor, sensory inputs, visual, auditory, etc., are mapped onto corresponding areas of cerebral cortex in an orderly fashion. So these neurons form a map that are known as topographic map, and these contain or has 2 important properties. At each stage of representation or processing, each piece of incoming information is kept in its proper context or neighborhood. So this means that when any of these sensory systems, like the auditory system, for example. When you perceive some information, this information is processed based on the characteristic of this input signal in a very localized part of the system. So information is localized when it is processed by these neuron systems. And second, the neurons dealing with closely related pieces of information are kept close together so that they can interact via short synaptic connections. So this idea of neighborhood appears in these biological systems in this way, that the neurons that are closer to each other process similar input vectors. And this idea is the one that was used for designing the self-organizing maps. So our interest is in building artificial topographic maps that learn through self-organization, and they are inspired by these neurobiological systems. So we shall follow the principle of topographic map formation. The spatial location of an output neuron in a topographic map corresponds to a particular domain or feature drawn from the input space. So the principal goal of a self-organizing map is to transform an incoming signal pattern of arbitrary dimension into a one or two-dimensional discrete map, most commonly two-dimensional, and to perform this transformation adaptively in a topologically ordered fashion. We therefore set up our SOM by placing neurons at the nodes of a one or two-dimensional lattice. Higher dimensional maps are also possible, but not so common, like a three-dimensional SOM. The neurons become selectively tuned to various input patterns, which is considered the stimuli, or classes of input patterns during the course of the competitive learning process. So we will focus specifically on the Kohonen networks. Okay, there are other kinds of self-organizing maps, but by far the most common one is the Kohonen networks. So this SOM has a feed-forward structure with a single computational layer arranged in rows and columns. Each neuron is fully connected to all the source nodes in the input layer. So in this kind of networks, we consider that we have two layers: the input layer, which are defined by some variables that will perceive the input information. Like in this case, we are considering that our points are in 5 dimensions, vectors of dimension or size 5. And our computational layer is a lattice of, in this case, 6 by 8 neurons. So we have 48 neurons arranged in a lattice. And every single input variable or input neuron is connected to each of the neurons in the lattice. Clearly, a one-dimensional map will just have a single row or a single column in the computational layer. Well, so if this would be an example of a Kohonen network in 2 dimensions. It is arranged in this square or rectangle, and if you implement this in a one-dimensional map, then what you would have is only one row of these neurons. So maybe you want to use also 48 neurons in only one row. So you will have a row with 48 neurons. So what is the difference between using a 2D or a one-dimensional map? When you use a 2D map and one of the neurons is the winner neuron, the neighborhood is defined in, let's say, in 2 dimensions. So you can look for the closer neighbors, in this case to the left, to the right, up and down, and you can generate like a circular or a square-like neighborhood. And the neighborhood, as you will see, is important to make the neurons closer to the activated neuron to become similar to the activated neuron every time you feed the network with a new vector. If instead of using a 2D arrangement you use only one row, so suppose that we're talking about this row as the only arrangement of neurons, if one of the neurons is activated, only you can look for neighbors to the left and to the right only. So possibly the impact of this neighboring, this localized learning will have less, or it will have a less impact than if you do it in a 2-dimensional. But for a specific task, you will need to run experiments to see what is better for your problem. So you cannot say from the beginning that a 2D will be better than a 1D. But usually what people tend to implement is a 2D map.